Assalamu alaikum dear students. In today's digital system design lecture, we are going to start from behavioral modeling. Learning objectives include define blocking and non-blocking procedural assignments, understand delay-based timing control mechanism in behavioral modeling. This includes regular delays, intra-assignment delays, and zero delay. Describe event-based timing control mechanism. This includes event control, named event control, and event hour control. Use level sensitive timing control mechanism. Now starting from procedural assignments. Procedural assignments update values of register variables, integer, real data type, or time variables. The value placed on a variable will remain unchanged until another procedural assignment updates the variable with a different value. These are different from continuous assignments discussed in data flow modeling, where we have used assignment operators and assignment keywords to place the value on the nets. Expression to be continuously placed onto the left hand side, which is net data type. While left hand side of a procedural assignment can be one of the following as reg register data type, integer data type, real or time register variable, or memory element. While in data flow modeling we have used assign keyword, which is used to assign the value to a connection or net data type. So please note the difference. Now left hand side of procedural assignment can be a bit select of these variables, such as for example address 0, a part select of any variable. Here you can see that we have select a part of a variable, a concatenation of any of the above. Now the right hand side of any procedural assignment can be any expression that evaluates to a value. There are two types of procedural assignment statements known as blocking and non-blocking. Blocking assignments are executed in the order they are specified in a sequential block. Here you can see that specified in A, here a space is required. A blocking assignment will not block execution of statements that follow in a parallel block. It means that if we are using blocking assignment statements and we are also using parallel block, then blocking assignment will not block execution of parallel blocks. Parallel block detail will be provided in coming slides. The equal operator is used to specify blocking assignment. Here you can see the operator is used, equal sign. This operator is used to specify blocking assignments. Now this is the example of blocking statements. Here x, y and z variables are used and they are selected as register data type. Here another variable register A and register B of 16 bit are declared. Here a count variable of integer data type is declared. Now please note an important point that all behavioral statements must be inside an initial or always block. We have to use initial or always block to use the behavioral statements. Now an initial block begin. Here x, y and z are initialized with the blocking assignment operator. Here you can see that this equal sign is known as blocking assignment operator. Here count variable is initialized with value 0 and register A, register B are vectors and initialize the values. Here you can see that hash 15 delay is used of 15 time units, and this variable bit number 2 is assigned the value 1 bit binary 1. Bit select assignment with delay, this is known as bit select assignment, and here delay is encountered. Here another command which include concatenation of x, y and z, and it is assigning to register B bit number 13 to 15 with 10 time unit delay. And here this blocking assignment operator is used to assign the value to a integer data type. Now as this is the blocking assignment, so when these commands are simulated, the statement y is equal to 1 is executed after x is equal to executed, because these statements are sequential in nature. As you see that we are using blocking assignment, so first x is equal to 0 will be executed, and after the execution y is equal to 1 is executed, and after that z is equal to 1 is executed in order, and after that all the statements will be executed in order. The behavior in a particular block is sequential in a begin and block if blocking statements are used. As explained earlier, that blocking assignment is sequential in nature, and these statements will be executed in sequence, and the last statement count is equal to count plus 1 is executed last. Now if we analyze the simulation time at which the statements are executed, now from start all statements x is equal to 0 through regb is equal to rega are executed at time 0. Here you can see that here this initial block starts. These statements without any delay will all be executed at time 0. Here you see that from x is equal to 0 to this statement regb is equal to rega, these all are executed at time is equal to 0. This statement will be executed at 15 time unit delay and this statement will be executed further 10 time unit, and total time unit will be 15 plus 10, 25 time unit delay. This statement will be executed after 25 time unit delay. Let's see in the next slide. Here you see that statement REGB is equal to XYZ will be executed at time 25, and similarly this statement have no time delay, so this statement is executed at 25 time unit, and this statement also will be executed at 25 time unit without any delay. Now procedural assignments to registers. If the length of the register variable is not equal to the assignment variable, here you can see that if the right hand side has more bits than the left hand side register variable, the right hand side is truncated to match the width of the register variable. This is same as if we are assigning a 32-bit number to a register variable of 16-bit number. So the right hand side 32-bit number will be truncated to match the width of the left hand side register variable. Similarly, the least significant bits are selected and the most significant bits are discarded. If the right hand side has fewer bits, zeros are filled in the most significant bits of the register variable. It means that if we are assigning the variable, let's a variable which is right hand side variable and has 4 bits, and this 4-bit variable is assigning to a number left hand side b which has 8 bits, then the right hand side number will append 4 zeros to match the width of the left side variable. Please note that if width is mismatching, then these scenarios will occur. Zeros are filled if left hand side variable bits are less, and if left hand side variable is more than the right hand side, then zeros padding or bits truncation will occur accordingly. Now we are here explaining about non-blocking assignments. These are used to allow scheduling of assignments without blocking execution of the statements that follow in a sequential block. The operator, this operator less than or equal to, used to specify non-blocking assignments. Note that this operator has the same symbol as we have used earlier in data flow modeling, known as relational operator. This operator is interpreted as relational operator in an expression and as an assignment operator in the context of non-blocking assignment. This operator, this symbol is also used in data flow modeling but here we are using this in non-blocking assignment. So in both cases it will be valid, as in behavior modeling this symbol will be used in always all initial blocks only, but in data flow modeling this symbol can be used anywhere without initial or always blocks. Now here an example is given to illustrate the use of non-blocking assignments. Here variables are declared as register data type and count as integer data type. Now initial block starts, and here you can see that a delay 15 time units is used, here 10 time units. Now as we know that when no delay is used, all these assignment operators, this is known as blocking assignment operator, these all will be executed at time 0. This statement will be executed, this is non-blocking, and it will be executed at 15 time units, and this is also non-blocking, so this statement will be executed at 10 time units. As you see that delay is independent in non-blocking assignments. If here we use blocking, then this, and here also blocking, then this statement will be executed at 25 time units, but due to non-blocking assignment this statement will be executed at 10 time units, and this non-blocking assignment will be executed at 0 time unit, because this is non-blocking and order will not be followed. Here you can see that this statement is executed at 15 time units, here 15 time units, and this statement will be executed at 10 time units, and this statement will be executed at 0 time unit, because we have used non-blocking assignments, so these will run parallel and no order will be followed. Now simulator schedules non-blocking assignment statement to execute and continues to the next statement in the block without waiting for the non-blocking statement to complete execution. This means that simulator will run these commands in parallel, this and this one will run in parallel, and simulator will not wait for this to execute and then this will be executed. So please note the difference, that in non-blocking assignment all the statements will run in parallel. Now this example include both blocking and non-blocking. Here you see these are the blocking assignments and these are the non-blocking assignments, but in practical it is not recommended to mix the blocking and non-blocking in same always block. Now if we want to discuss application of non-blocking assignments, now it is important to understand why they are used in digital design. They are used as a method to model several concurrent data transfers. Please note the important point that when a concurrent data transfer will occur after a common event, then a parallel execution is required. So for parallel execution, non-blocking assignment operators will be used. An example is given here. Here an always block is used, and this block will be executed at positive edge of clock. Now here you can see that when positive edge of clock occur, register 1 variable will be assigned in 1 with 1 time unit delay. Register 2 will be assigned in non-blocking assignment and will be assigned value when negative edge clock occur, and this is the XOR operation of in2 and in3. Here register 3 will be assigned non-blocking statement, register 1 with 1 time unit delay. These all three statements will run in parallel, and these time delay units will be followed. Now the detail of these execution of statements, a read operation is performed on each right hand side variable in 1, in 2 and in 3. Here you can see that although this delay is encountered here, but read operation will be executed of all three statements at time 0, and read operation when the positive edge of clock occur, then read operation will be performed. Now right hand side expressions are evaluated and results are stored internally in the simulator. Here when positive edge clock occur, this in 1 read out by simulator, this in 3 read out by the simulator without any delay. So all three statements read out operation will occur at the same time. Right hand side operations, and results are stored internally in the simulator. The write operations to the left hand side variables are scheduled to be executed at the time specified by the intra-assignment delay. This delay type is also known as intra-assignment delay. Now explanation of this example. Include here this example will be followed. Now the write operation to the left hand side variables are scheduled to be executed at the time specified by the intra-assignment delay, that is scheduled write to reg1. Here schedule write to reg1 after 1 time unit, schedule write to reg2 when the negative edge of clock will occur, and schedule write to reg3 after 1 time unit, and the value will be reg1. This is also the old value of reg1, because for this command simulator read this value at the same time. All of the three commands occur when the positive edge of clock is executed. Schedule write to reg1 accordingly. the write operations are executed at the scheduled time steps. The order in which the write operations are executed is not important because the internally stored right hand side expression values are used to assign to the left hand side values. Here you can see that these non-blocking assignments, when positive edge clock occur, the read operation will be performed at the spot for all the commands, and after the concurrent read operations, then this delay and this event will be followed accordingly, but read operation will be executed at the same time for all the three statements. So reg3 is assigned the old value of reg1 that was stored after the read operation, even if the write operation wrote a new value to reg1 before the write operation to reg3 was executed, because as this read operation is performed simultaneously, so after one time unit this reg1 will be updated, but read operation have been encountered before, so this reg3 will have the old value of reg1 but not this in one which will be assigned to reg1. Now another example which is related to swap the values of a register A and B at each positive edge of clock using two concurrent always block. This example used non-blocking statements to eliminate race conditions. Race conditions are about to assign the value at non-deterministic manner. It is a reading assignment. You can read itself, but submission is not mandatory. Now here an always block is used, and at positive edge of clock A is equal to B is assigned, and this is another always block. Please note that no begin and end is used because only one statement is used here. Now in these always blocks, these two always blocks will be executed at time 0. Now this is the race condition because for the simulator it is non-deterministic that whether this A is equal to B will be executed first or this B is equal to A will be executed. Here you can see that two always blocks are used, and here we are using non-blocking assignment. In one, there is a race condition when blocking statements are used. Either A is equal to B would be executed before B is equal to A or vice versa. Here you can see that here A is equal to B assigned because blocking. So although these are always blocks, but in blocking assignments it is not deterministic that this will be executed first. Execution will be completed first for this or this, but due to always block these both will be started at time 0. Now here, depending on the simulator implementation, values of register A and B will not be swapped. Instead, both registers will get the same value, previous value of A or B, based on the Verilog simulator implementation. Please note the difference that in this type of blocking assignments, race condition will occur, and this may happen that value of A and B will not be swapped. But in the case of non-blocking assignments, at the positive edge of clock, the values of all right hand side variables are read, and the right hand side expressions are evaluated and stored in temporary variables. Here you can see that when this positive edge of clock will occur, read operation will be performed, and this B is stored in a temporary variable, and this A will be stored in temporary variable, and after that the values from the temporary variable will be assigned to A and B, and the swap operation will be performed. During the write operation, the values stored in the temporary variable are assigned to the left hand side variables. Separating the read and write operations ensures that the values of registers A and B are swapped correctly, regardless of the order in which the write operations are performed. Example shows how non-blocking assignments in illustration 2 could be emulated using blocking assignment. This means that another example is given here, that if we want to swap the values properly using blocking assignments, then we have to use a temporary variable. Here you can see that first we have to store this in temporary variable A and store variable B to temporary variable B, and after that we have used these commands so that in this way no race condition will occur and a properly swap operation will be performed. Now, for detailed design, use of non-blocking assignments in place of blocking assignments is highly recommended where concurrent data transfers take place. Concurrent data transfer means that a parallel event of data transfer will occur. In such cases, blocking assignments can potentially cause race conditions because the final result depends on the order in which the assignments are evaluated. Non-blocking assignments can be used effectively to model concurrent data transfers because the final result is not dependent on the order in which the assignments are evaluated. Typical applications of non-blocking assignments include pipeline modeling and modeling of several mutually exclusive data transfers. On the other side, non-blocking assignments can potentially cause a degradation in the simulator performance due to parallel execution and also increase in memory usage.